So today we will discuss different types of addresses. So it will be the part of uh, network basics or introduction to networks. So in addresses, first of all, let's discuss an address which is called as MAC address. So MAC address size is 48 bits and it is written in the form of 12 hexadecimal numbers. So when we are talking about different formats, let's say 000.111.222. So these are 12 hexadecimal numbers in three portions of uh, 4 hexadecimal numbers which are separated by dot. The second possible option is we can write down it as 00, colon 00, colon 11, colon 11, colon 22, colon 22. So this is the second valid format that you can write down these 12 hexadecimal numbers in the part of 22 hexadecimal numbers, 6 parts of 22 hexadecimal numbers separated by colon. Then the second valid format is 00 hyphen 00 hyphen 11 hyphen 11 hyphen 22 hyphen 22. So this is the third valid format. So usually you can see this one on the Cisco devices, this one you can see on the open source Linux, Unix, and this one you can see on the Microsoft. So it is guaranteed that this address is a unique address. So that guarantee is based on the fact that we can divide this address into two parts. The first 24 bits or 6 hexadecimal number, so that is called as OUI, and the next one, next 12 6 hexadecimal numbers, 24 bits, is called as vendor assigned. So OUI, organizational unique identifier, and the second part is called as VA, vendor assigned. So OUI is assigned by IEEE to the vendor as a registration number, and the same registration number cannot be assigned to two vendors by IEEE. So this is the serial number of the devices. So no vendor can make two devices of the same serial number. That's why it is guaranteed that this is a unique number. Other than this, 01005E. So the MAC address starting with this one are IPv4 multicast address. So this is the MAC address for the IPv4 multicast address. OUI for the of an IPv4 multicast address. In the same way, if there is some MAC address starting with 33, so this is OUI for the multicast MAC address of an IPv6 multicast address. So when we proceed, I will tell you how to calculate these addresses. Right now, if you see this MAC address, you have to be familiar with that this is for IPv6 multicast, this is for IPv4 multicast. Then we have another one, FFF. So this is the broadcast MAC address. So after the MAC address, we quickly discuss the IPv4 address. IPv4 address is an address of 32 bits. So written in the form of 4 octets, 4 portion of 8 bits. So one portion of 8 bits, so it can have a value of 0 0 0 0 0 0 0 0 to 1 1 1 1 1. If all these values are zeros in decimal, we can write it as 0. If all these values are 1, we can write it as 255. It means in one octet, we can have a value from 0 to 255. A 32-bit value or IP address is divided into 2 parts. The first part is called as network portion, and the second one is called as host portion. So here we need to discuss the IPv4 message types. IPv4 message types includes, the first one is called as unicast, the second one is called as multicast, and the third one is called as broadcast. So unicast. So unicast one-to-one communication. One-to-one communication, one sender, one receiver. So that is called as unicast. Multicast, one to a group. So one to many or one to a group. So one sender, a group of users are the receivers. So one to any. One to any means whoever have the capability to receive can receive it. So one sender is just broadcasting without specifying whoever will have the receiving capability can receive it. So in the same way, when we say IP addresses, so IPv4 addresses are divided into 5 classes. The first class, class A, class B, class C, so those are the unicast addresses. Class A, class B, class C, class D, class E. So first 3 classes are for the unicasting or the unicast. So they contain the IP addresses for unicast. So class D is for multicast. So class E was undefined, and we have a global broadcast address. So undefined, its purpose was not defined. So global broadcast address 255, 255, 255, 255. So when we say IP address is divided into 2 parts, so we are talking about first 3 classes. So class A, class B, class C. IP address is divided into 2 parts. The first one is called as network portion and host portion. So each class has different size of the network portion and host portion. So we'll discuss it. But right now, 32 bits 4 octet value can be one of the following. The first option is network ID. The second one is broadcast ID. And another option is IP address. Another option is subnet mask. Another option is wildcard mask. So when we are talking about IP address, so we keep these two a little bit separate. So network ID. If all host portion bits are set to 0, so that address is called as network ID. If all host portion bits are set to 0, that is called as network ID. Broadcast ID. If all host portion bits are set to 1, so that is called as broadcast ID. If host portion bits are combination of zeros and ones, so that is called as IP address. In the same way, subnet mask network portion bits are set to 1 and host portion bits are set to 0. So in subnet mask, 1 is match, 0 is ignore. Wildcard mask, so network portion bits are set to 0 and host portion bits are set to 1. So here we can say 0 is match and 1 is ignore. In OSPF, in EIGRP and ACLs, so there are some configurations where instead of subnet mask we use wildcard mask. But again, in the all latest operating systems, like in the firewall operating systems and other ones, they are not using wildcard mask anymore. So they are just using subnet mask. So first of all, we need to understand why we use subnet mask. So can anyone tell why we use subnet mask? Any idea? Use of subnet mask. Subnet mask is used to decide the type of communication. Type of communication. The first one is local communication. I'm not typing itself. Itself is if you want to ping your own IP or if some service is running on the local machine. So that is itself. But right now we are not going for itself. We are just we discuss the local and remote. So local communication. And the second one is called as remote communication. The first one is the local communication. The second one is the remote communication. Local communication means destination is within the same network. So if the destination is within the same network, that is local communication. And if the destination is off net, means outside of the network, in some other network, so that is called as remote communication. So if the communication is local, so OS looks OS performs the R cache lookup to find out the MAC address of the destination. If R cache lookup failed, so then it can just send an ARP request and will get ARP reply. The second option is destination is off net. So OS looks into systems routing table. So this is the first step, and after that OS performs R cache lookup to find the MAC address of gateway. Because when we configure the gateway IP address on a system, then our route is added into the system's routing table. If we do not configure the gateway IP, then that route is not added and your system cannot communicate outside of the network. So OS performs the R cache lookup to find the MAC address of the gateway. So let's say we have an IP address 10.0.0.1 and its subnet mask is 255.0.0.0. So 10.0.0.1. So let's say this is the source IP address. So then we have a destination IP address. So destination IP address is 10.0.0.2. So what we do is we will write down into the binary. So for 10, 128, 64, 32, 16, 8, 4, 2, 1. So this is 10. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is your 10.0.0.1 in the binary. So subnet mask network port 255.1.1.1 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. If each bit is multiplied to its corresponding bit, so then when we have 1 in the subnet mask, so those bits will come as it is, because 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 1, 1, 0, 1, 0. And when whatever the value in the host portion, when it multiplied to the 0, it becomes 0. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So let's say we have multiplied the source with its subnet mask. And if we multiply the destination, so destination is 2. So we make it 1, 0. So when we multiply 10.0.0.1 to its subnet mask 255.0.0.0, so we get the network ID, and the network ID is 10.0.0.0. In the same way, the destination is 10.0.0.2 and the subnet mask is 255.0.0.0. So when we multiply it, we get 10.0.0.0. So when we multiply the source IP and destination IP to its subnet mask, so we get the source network ID and we get the destination network ID. If the source network ID and destination network ID are same, it means communication is local. Let's say we have another communication. In that communication, I'm gonna make it 11.
Sir, sorry, I had raised my hand as well.
So it will become 11.001. When multiplied, it will become 1100. So if it is 11002, sorry, let's make it 10. We keep it 10,002. So this time 1100, 10,000. It means source and destination network IDs are different. So then the communication is remote. So if network source and destination network IDs are different, then the communication is remote. So now we will discuss the types of IP addresses. The first one is called as public IP. The second one is called as private IP. The third type is special use. So public IP, the IP address is used to communicate over the internet. So IP address is used to communicate over the internet. These are called as public IPs. So IP address is used to communicate within the LAN. So those are called as private IP addresses. Special use IP addresses. So these are not either public or private. So when we will discuss these IP addresses, then we will discuss them again, that what are those addresses which are called as special use. So class A, if the first octet value is from 1 to 127, so then all those addresses belongs to class A. So why it is, let's say 1. So 1, 2, 3, 4, 5, 6, 7, 8. This is your 1. So 0, 1, 2, 3, 4, 5, 6, 7. So this is your 127. So you can see in both addresses or both values, the first bit is fixed to 0. If the first bit remain fixed to 0, so all those addresses belongs to class A. So let's say if we write down an address 10.001. So this is an IP address. So we have to look for the first octet value. It is between 1 and 127. So it is between 1 and 127. So it means that this belongs to class A because it is from 1 to 127. So now this address has two portions. The first address, first 8 bits belongs to the network portion, and the last 3 octets, so those belongs to the host portion. In if we want to write down the subnet mask, so we said the network portion bits are 1. If 8 bits are 1, it is 255. In subnet mask, host portion bits are 0. So we make it 0.0.0. So 10.001, 255.0.0.0. So this is the default subnet mask of class A. So private IP address range in class A. So private IP address range, all the addresses starting with 10, so those are private IP addresses. So 10.000/8, so this network is private. A special use IP address. So special use IP address is 127.0.0/8. So this is reserved for loopback testing. So we use 127.0.0.1 as a local host. If you want to verify your communication with your protocol stack and network interface card, you can use this IP address 127.0.0.1 or ping localhost. So number of hosts in a network, so you can calculate it by using a formula 2 raised to the power number of host bits. So whatever the result is, subtract 2. So one network ID, one broadcast ID. Those cannot be assigned to any device. So that's why we subtract those two. So 2 is for number of host bits minus 2. So in our case, we have 2 raised to the power 24. Whatever the result will come, you will subtract minus 2 and you will get the, so you have more than 1 million hosts in class A network. Not 1 million, I think it is more than 4 million hosts in class A network. Then in the similar way, the second class is class B. If the first octet value is from 128 to 191, then it means that those addresses belongs to class B. So if we write down them in the binary, so 1000, if we fix the first two bits to 10 and change all rest 6 bits to 1, so this value is 128, the second value is 191. So you can see the first two bits are fixed to 10. If we fix first two bits to 10, all those addresses belongs to class B. Let's write down an address 172.16.0.1. So 172, it is between 128 and 191. So when it is between 128 and 191, so it means this address belongs to class B. So class B, again, this is a unicast IP address class, so that's why we can divide it into two portions. The first 16 bits are the network portion and the last 16 bits are the host portion. If we want to write down the subnet mask, so in subnet mask, network portion bits are 2511, so 255, 255, and host portion bits are 00. So this is the default subnet mask for class B. In class B, private IP address range. So private IP address range 172.16.0.0/12. So subnet mask is 16 bits, but when we want to write down the complete range of private IP addresses, we can write it down as 172.16.0012. So what does it mean? The first 12 bits must have to be 172.16. So these are 8 bits, 172, 8 bits. So next 4 bits, so we cannot separate from 16. We have to convert the 16 into the binary. So 128, 64, 32, 16. So these are 4 bits. 8 plus 4, 12. And then rest of the bits are 0, dot 0, dot 0. So first 12 bits are fixed. So if we keep these 12 bits fixed to 172.0.0.1 and we keep on changing the next 4 bits, so we will be getting different networks. So 172.16.0.0/16, this is the network. And then if we keep 172.0.0.1 and we change it to 0.0.0.1.0.0, so 172.17.0.0/16. So if we will keep on changing and these addresses, so the last possible combination with 172.0001 is 111. So it becomes 172.31.0.0/16. So all these 16 networks starting from 172.16.00 to 172.31.00, all these 16 networks are private. But when we have to write down in an integrated form, so we can write down it as 172.16.0012. Special use address. So special use address 169.254.0.0. So this is the network which is /16, which is reserved for DHCP clients, and this address is also called as APIPA, automatically assigned private IP address. So this address can only be used to communicate with DHCP server. Other than this, this IP address cannot be used for any other communication. So we have two types of network interface cards. The old network interface cards are called as non-PXE clients, PXE pre-execution environment. New network interface cards are called as PXE clients. Non-PXE client, which is not boot capable, so cannot be used as first boot device. So PXE client boot capable can be used as first boot device. So when a network interface card cannot be used as the first boot device, it means we can configure it as DHCP client. We can configure it as DHCP client. When your operating system will be loaded, so you can select obtain IP address automatically, it will become DHCP client. So DHCP client gets the IP address from this network 169.254.00/16. So PXE client. So PXE client can use boot P or DHCP. So when operating system is not loaded, so then it sends boot P request. It does not send the DHCP request. So boot P request can be sent. So it is not DHCP client. When it is not DHCP client, it cannot use 169.254.0.0 by default. It will use an IP address 000 to communicate with DHCP server. If DHCP server is found, so DHCP server will assign an IP address. So it will renew that IP address for itself and it will start using that one. But if it fails to get, or if it fails to discover DHCP server, so then it gets a PIPA, automatically assigned private IP address. So initially it tries to get it gets 000, it uses 000 to communicate with DHCP server. If it will fails to found or fails to discover DHCP server, so then it will get and it will show you limited connectivity, yellow sign on your network interface card. Then we have class C. If the first octet value is from 192 to 223, so 192, 110, and then 1, 2, 3, 4, 5. So this is 192. If we fix 110 and then all rest of the bits becomes 1, so it is 223. It means if the first three bits are fixed to 110, so then all those addresses belongs to class C. So let's write down an address 192.168.1.1. So this is an IP address. We have to look for the first octet value. It is 192. It is from the range of 192 to 223. So from here we will found that this address is class C. So when it is class C, in class C, one octet belongs to the host and first three octets belongs to the network. So network and the last octet is host. So if we want to write down the subnet mask, in subnet mask network portion bits are 1. So when 8 bits are 1, it is 255, 255, 255, and host portion is 0. So this is the default subnet mask for class C. So private IP address range So private IP address range 192.168.0.0/16. So what does it mean? From 192.168.0.0/24, 192.168.1.0/24, up to 192.168.255.0/24. So all these addresses, 256 networks, are private. So special use address 192.0.2.0. So this network is reserved for documentation and example. So whenever you need to use some public IP in your example, in your documentation, then you can use this one. There are some more 192 networks which are special use, but this is the main one. So if we want to calculate the number of hosts, so we missed here as well. So number of hosts, if we want to calculate number of hosts, the formula is 2 raised to the power number of host bits. So in this case, in class B, it is 2 raised to the power 16 and then minus 2. So it is 65534 hosts or host addresses possible in any class B network. Host addresses, IP addresses. If we want to calculate the number of hosts in class C, then the formula is 2 raised to the power number of host bits. Here number of host bits are 8. So we can have 254 host addresses or IP addresses. So these first three classes are used for unicasting over the internet or networks. So then we have class D. So class D is used for multicast. So if the first octet value is from 224 to 239, 2241110. If first 4 bits are fixed to 110, remaining 4 bits are 0, it is 224. If first 4 bits are 110 and remaining bits are 1, so this one is 239. So if the first octet value is from 224 to 239, then that address belongs to class D. So class D is used for multicast. So each address represents a group. So each address represents a group. So there is no network portion, there is no host portion. So class D addresses are further divided into different categories. The first range is 224.0.0.0/16. So if your address is starting with 224.0/224.0, so then these are local subnet, well-known multicast address block. So local subnet means 224.0.0.1. So this is reserved for all hosts on a subnet. If you want to send a message to all hosts on your network, you can use this address 224.0.0.2. All routers on a subnet. 224.0.0.5. All OSPF routers on a subnet. So these are the examples of this first group. Then we have 224.1.0.0/16. So this is internet scope. well-known multicast address block. So Internet Scope, well-known multicast address block. So other than this, we can have some other well-known blocks. So those well-known blocks includes, so Internet Scope, well-known multicast address block. After this, we have 232.0.0.0/8. So this one is SSM default. SSM default means source specific multicast. When we discuss the multicast, we will have two types of multicast distribution trees. One is called as source tree, the other one is called as shared tree. So this one is usually used for source tree. 239.0.0/8. So this is locally administered address block. So we can use it for ASM, any source multicast. So anyway, we will discuss these things later on in more detail when we cover the multicast topic. So now we will see how to calculate the multicast MAC address for an IPv4 multicast address. So multicast MAC address. So first of all, let's say we have an address 225.1.1.1, 225.1.1.1. So what we have to do is the first step. So we use 01005E as the OUI, organizational unique identifier. Second step, convert the last 23 bits of IPv4 multicast address. So convert the last 23 bits of IPv4 multicast address into hexadecimal numbers. So this is your IPv4 address. So 225 dot. So I haven't changed the first 8 bits. Now I will convert the last 24 bits. So 0, we have to use 23. That's why I'm gonna make it separate. So 0000. One hexadecimal number is 4 bits. 0001, 000, 001, 000, 0001. So basically, now we have converted, we have to use the last 23 bits. We have to convert them into the hexadecimal numbers. So we can write down it as 01005E instead of 255. Now we have to write down these two numbers. So these all are 0. So we put it 0. So this is 0001. Hexadecimal number is 1. Next one is same 0000, 00001, 1. 0000, 0001, 1. So in this way, we have calculated the multicast MAC address for an IPv4 multicast address. So there is a 32 by 1 overlap between the IPv4 addresses and MAC address. For 32 IPv4 multicast addresses, we have the same MAC address. Let's say if you make it 224, rest are 111. So 224, 225, 226, 227, 228 up to 239. So there are 16 values. So these are 16. Then if you make it the second octet value to 129. So again, this bit will become 1 and the last is 1. We are not considering this bit. Again, we have 16 more multicast IP addresses. So that's why we said 32 by 1 overlap. 32 IPv4 multicast addresses uses the same MAC address. Class E.
Sir, any specific reason for this thing?
Basically, the way we are converting it, we are converting last 23 bits into hexadecimal numbers. So last 23 bits are 32 IPv4 multicast addresses. It is same 010101, 224 111, 224 12911, 225 111, 225 12911, up to 239111 and 239129111. So they are having same last 23 bits. That's why this is an overlap. And it is very rare, very rare chances that you are using the same IPv4 address which is overlapping with this one in your network. Let's say you are using SSM. So there are only two overlapping, 232.111 and 232.129.111. Again, a very big gap. Very rare chances you will be using both ones. If you're using ASM 239 address block, again, there are only two addresses overlapping to each other. So that's why it does not create any problems.
Right, sir.
So class E 240 to 255. If the first octet value is 240 for 240, so we say 111, 4 bits are fixed to 1 and 4 bits are 0. If we keep 4 bits to fixed to 111 and we make the rest of the 4 bits to 111, so it is 255. So this class was kept defined later on, but before that time, unicast IP addresses were facing the shortage. That's why they moved towards IPv5. IPv5 address was 64 bits. So when they noticed the rapid growth in internet, so then they assumed that again IPv5 addresses will be face the shortage very soon. So that's why they stopped that project IPv5 and moved towards IPv6 128-bit address. So here we have 255.255.255.255. So this one is called as global broadcast address. So this one is the global broadcast address. So all other of the addresses remain unused. So some people say that 242 addresses were used by NASA, this and that. But again, we will consider it as undefined. So IPv4 address configuration options. So can anyone tell how IPv4, when IPv4 address is assigned, it performs duplicate address detection. So what is the duplicate address detection process of IPv4?
Are you asking question?
Yes.
So probably it's gonna do an ARP or ICMP for the IP address it's going to get from the DHCP.
No, we are just talking about duplicate address detection. When we configure static IPv4 address, does it perform duplicate address detection or not? Okay, so first of all, let's go to the simulation mode, show all none, edit filters, ARP. So ARP is used for duplicate address detection. If we go to this PC, desktop, and I say 192.168.1.10 and tab, so it has generated an ARP packet. If we open this ARP packet, so you can see destination is broadcast MAC address. And if you have a look on the type 806, 806 is ARP. OP code 001, it means this is ARP request. So this is the source MAC, sender IP 1.10, target MAC 000, target IP 1.10. So this host is sending an ARP request against its own IPv4 address. So this thing is called as duplicate address detection. So when we forward it, this message is broadcasted over the network. So all these PCs will receive the message. No, none of these PCs are using the same IP. That's why they have discarded the ARP request. So when the ARP request will time out, it means no one is using this IP address on the network. So this thing is called as duplicate address detection. So the first option is static IPv4 address configuration. So for static IPv4 address configuration, we have just configured this IP address. So when a system gets an IPv4 address, it generates an ARP request for its own IPv4 address. If some system is using that IP address, it sends ARP reply. It sends ARP reply. If all systems, or if any system is not using that IP address, then ARP request times out. It means no one is using that IP address. So ARP is used to perform duplicate address detection, whether you get an IP address statically or manually, or you get through the DHCP. So if we go to the router, interface fast Ethernet 0x0, IP address, 1.1, 255, 255.0. No shut and exit. So you can see so broadcast 806.11.11. So no one is using, it means this is not a duplicate address. The second option, if we configure the DHCP server on this device, let's say IP DHCP pool LAN. So our network is 192.168.1.0, 255.255.255.0. Default router is 192.168.1.1, and then we say DNS server is, let's say, 888, and exit. So we go to this PC, edit filters. I'm going to enable DHCP. DHCP. So this is the DHCP discover message. When this DHCP discover message is received, so now router has to offer some IP address. But before that IP address, DHCP is offering IP address, DHCP server will perform the duplicate address detection. It is looking for 1.2 because its own IP address is 1.1. It has to offer 1.2. So DHCP server is performing the duplicate address detection. So when the request will time out, so now it is offering that IP address 1.2, 1.2. So when this DORA process completes, then the host will perform the duplicate address detection again. So now it is gonna ask my IP 1.2. If anyone else is using 1.2, send your MAC address. So DHCP server performs duplicate address detection, and when the host gets the IPv4 address, it also performs the duplicate address detection.
Is there any specific reason for this happening at two places?
Yes, it is to make sure, because in the host configuration, it is written that whenever a host gets an IP address, it has to perform the duplicate address detection. Sometimes DHCP server is not local to the subnet. So then DHCP relay, but
Oh,
again,
okay.
yeah,
Yes. Thank you.
welcome. So both have to perform the duplicate address detection. So this is for now IPv4. If you have any questions from IPv4, we can discuss, or let's quickly have a look on the subnetting, because we cannot complete IPv6 today. So we will start IPv6 tomorrow. So in the meanwhile, uh, there are two types of subnetting. One is simple subnetting, one is variable length subnet masking. Subnetting, if we need all subnets of the equal size, we do the subnetting. If all the subnets are not of equal size, we need the subnets of different sizes, then we go for VLSM, variable length subnet masking. But let's say I will give you two examples of both. So 200.110/24. So we want to subnet it. So by default, this network has 254 hosts. So our requirement is 60 IP addresses. So our requirement is 60 IP addresses. So what we'll do is we will convert the host portion to binary. So 1, 2, 3, 4, 5, 6, 7, 8. So each bit has a value. This first bit's value is 1 to 8. Next one is 64. Next one is 32. 16, 8, 4, 2, 1. So our requirement is 60. So we have to look for 60 on this scale. 60 is between 64 and 32. It means we have to extend the network quotient 2 bits up to the higher bit value where your requirement lies on this scale. So it means we have to do the subnetting of 2 bits. So we have to separate these two portions. So now this portion, these 2 bits will be added to the network portion, and we will have 6 bits left for the host portion. So now we have to calculate the number of subnets. So to calculate the number of subnets, the formula is 2 raised to the power number of subnet bits. So we are doing the subnetting of 2 bits, 1 and 2. So that's why we can write down it as 2 raised to the power 2. So result equals to 4. It means we will have 4 subnets. Now we have to write down the possible combinations in those 4 subnets. To write down the possible combinations, so we have to divide the maximum number of subnets, so the subnets divided by 2. So we will get reply 2, and we will keep on dividing the result by 2 until we get 1. So the first result is 2. 2 means under the first bit we have to write down 2 times 0 and 2 times 1. 0, 0, 1, 1. So these are the 4 subnets. Then the next result is 1. It means in the next bit we have to repeat 0 and 1. 1 times 0, 1 times 1. 0, 1. 0, 1. So if all rest of the bits are 0, so we can just write down the network ID. So 200.1.1 dot, the first one is 0, 0, 0, 0 / 26. 2 bits are added into the network portion. 24 plus 2, 26. So the first subnet becomes 200.110 / 26. In the second subnet, this bit value is 64. So we can write down 200.1.1.64 / 26. So 200.11. So this bit's value is 128 / 26. 200.1.1.192 / 26. So we have write down the 4 subnets. So if the first subnet is starting with 0, the next one is starting with 64. So this is your network ID. So broadcast ID becomes one before the next network ID, 63. So this one becomes your broadcast ID. So IP addresses are from 1 to 62. So 62 IP addresses are possible in this subnet. So 62 IP addresses are possible in all these subnets. The second network's broadcast ID becomes 200.1.1.127. The next network's broadcast ID 200.1.1.191. Next network's broadcast ID 200.1.1.255. Last one is we know it is 255. So all these networks have the 62 IP addresses. In the first one, network ID 0, broadcast ID 63. So IP addresses are from 1 to 62. The second one 64 to 127. So 65 to 126 are IP addresses. 128 to 191. So 129 to 190 are the IP addresses. 192 to 255. So 193 to 254 are the IP addresses. So all these networks having the 62 IP addresses, and our requirement is 60 IP address. So this is how you can do the subnetting. So one example of VLSM variable and subnet masking. So we have the same network 200.1.1.0/24. So our requirement is we need one subnet of 60 IP addresses. We need two subnets of 30 IPs. We need four subnets of 14 IPs. We need 8 subnets of 6 IPs. So 60 plus 60. So 60 plus 60, 120. 120, 14 into 4. So let's make it 64. So it's not 64, but let's say it is 56. So 120 plus 56, 172. 120 plus 76, 176. 176 plus 8 into 6, 48. So it is below 254. It means it is possible to calculate. So now what we will do is we will choose the scale. So first of all, we have to look for the highest number of IP addresses, which is 60. For 60, we have to do the subnetting of 2 bits. So when we do the subnetting of 2 bits, so possible combinations are 0, 0. So second possible combination is 0, 1. Then we can have 1, 0. And then we can have 1, 1. So these are the 4 possible subnets. The first one is 200.1.1.0/26. The second one is 200.1.1.64/26. So 200.1.1.128/26, 200.1.1.192/26. So these are the 4 subnets of 62 hosts. So what I will do is I'm gonna give this last one to the customer with the requirement of 60 IP addresses. So it means now this one is unavailable. So next available is 200.1.1.128. So what I can do is I can choose any of these, but just to keep the calculation simple, I have given, because if I will start doing the subnetting of 8 subnets of 6 hosts, into this one 192. So I have to do the calculation of over 192. So that's why I give it to the customer, which require one subnet of 60 IP addresses. Second one, two subnets of 30. I will use this one, the second one, 200.11.128. So if we use the second one, 200.1.1.128 slash 26, it is already 26 slash 26. So if we write down it in the binary, so 200.1.1. So 10. So this is already the part of the network. So then we have 1, 2, 3, 4, 5, 6. So these 6 bits are available for subnetting. If
So
these
you could have given 192 the other ones, any of the other ones to the
we
first
can
one.
give any one of the that is, but if I will do this one, this fulfill this requirement, 8 subnets of 6 IP addresses, then I will have to do a lot of calculations here in 192. Just to keep it simple for myself, I given this one to the customer, which requires 60 IP
Right.
addresses.
Okay.
So now 128.64 are not available. So this bit's value is 32. So next one is 16. So now our requirement is 30 IP addresses. Second requirement is two subnets of 30 IP addresses. So 30 is between 16 and 32. It means we have to do the subnetting of one more bit. So when we do the subnetting of one more bit, we can have two possible combinations. It can be 0 or it can be 1. And then I will have rest of the bits as it is. So when I say it is 0 and 1, so I will write down it 200.1.1.100, and then rest of the bits are 0. So when I write down 200.1.1, and it was 10 before subnetting, so I will make it 1 and I will keep rest as 0. So if I convert it into the decimal, so this one becomes 200.1.1.128 slash 27, and the second one becomes 200.1.1.160 slash 27. So in this way we have two subnets of 3030 IP addresses. So we can give these two subnets to the customer, which require two subnets of 3030 IP addresses. So this requirement fulfill here, this requirement is fulfilled here. So now these are not available anymore, and this one is not available as well. Next available is 200.1164. So 200.1164, for 64 it is 01 slash 26 01. So 1 2 3 4 5 6, next 6 bits are 0. So now we have to look for the requirement. So this bit is 32, next bit is 16, 8, 4, 2, 1. 32, 16, 8. So our requirement is 4 subnets of 14. It means we have to do the subnetting of another 2 bits. So those 2 bits are this 32 and 16, because 14 is between 8 and 16. So what are the possible combinations? So 200.1.1.01. So this is already the part of the network. So we can consider this is the first combination. It can be 0, 0. Then 200.1.1.01. It is already network portion. It can be 0, it can be 1. So 200.1.1.01. This can be 1, this can be 0. 200.1.1.01. So this one is 1, the other one is also 1. So if we write down these values, so we can write out 200.1.1.64/28 because it was already 26. When we add 2 more bits into the network, it becomes 28. The second one becomes 200.1.1.80/28. 201.1.80 plus 1696/28. 1.1.112/28. So these are the 4 subnets with 14 hosts. So in this way we have fulfilled this requirement, the third requirement as well. So we will give these subnets to fulfill this requirement. Now this one is not available anymore. So this 200.110 is available. So we can write down 200.1.1.00 1, 2, 3, 4, 5, 6. So this one is 32, 16, 8, 4, 2, 1. So 32, 16, 8, 4, 2, 1. So now we are looking for the requirement. Our requirement is 66 IPs. So 6 is between 8 and 4. It means we have to do the subnetting of 3 more bits. 32, 16 and 8. So if I write down the combinations, so the possible combination can be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are 8 possible combinations. So if we want to write down them, the first one is 200.1.1.0/29. 26 was already 26 plus 3, 29. 200.1.1.8/29. 200.1.1.16/29. 200.1.1.16 24/29. 200.1.1.32/29. 40/29. 48/29. 56/29. So these are the 8 subnets with 66 hosts. So in this way we can fulfill this requirement. So 8 subnets of 16 hosts. So this thing is called as VLSM, variable length subnet masking. That we do the subnetting and then according to our requirements we keep on doing subnetting within the subnetting, so that we can have the different the subnets of different sizes from the same major network. Now you can see this customer is using with /26, this customer is using with /27, this one /28, and this one is using /29. So all they are using the subnets of one major network 200.110/24 with different subnet masks. So that's why we call it as variable length subnet masks. So we keep up to here today. If you have any questions, you can ask now.